Hello, and welcome back to Teacher Gibble's channel. Today I'm going over Illustrative Math, Algebra 2, Lesson 2, Practice. If you like this video, please make sure to like and subscribe to get more like this. Let's get started. Problem 1. Here are the first two terms of a geometric sequence, 2, 4. What are the next three terms? Well, when we have a geometric sequence, we're multiplying each of the terms by something to get the next term. So to get from 2 to 4, we multiplied by 2. So we're just going to multiply the next term by 2. 4 times 2 is 8. 8 times 2 is 16. 16 times 2 is 32. 64, 128. We can keep going, but we only asked for 3 terms. Problem 2. What is the growth factor of each geometric sequence? So because it is a geometric sequence, we're looking for something that we multiply to get the next term. Well, in this case, I'm going to say 1, because 1 times 1 is 1. 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 So the growth factor is going to be 1. To get from 256 to 128, I'm pretty sure I divided that by 2. And then 128 to 64, I definitely divided by 2. And I'm going to say multiply by 1/2. 18 to 54, 54 to 162. In this case, I believe that I multiplied it by 3, because 18 times 3 is 54. 54 times 3 is 162. So my growth factor is 3. 0.08 to 0.8 to 0.08 to 0.008. The decimal moves over each time, so I'm multiplying by 1/10. So I'm going to write it like this, or you can write your growth factor as 1/10. Here, we're going in the opposite direction. Our decimal points are getting bigger, closer and closer to the number, getting us bigger. So our growth factor is 10. We are multiplying by 10. All right. There we go. That's question 1 and 2. If you need to review it before moving on, make sure to pause the video so you have a chance to review. Problem number 3. A person owes $1,000 on a credit card that charges interest at a rate of 2% per month. Complete this table by showing the credit card balance each month if they do not make any payments. Okay, so the first month they owe $1,000. The second month they owe $1,002. The reason for this is because it's the original $1,000 times 0.02%. The 1 represents original owed, and the 0.02%, which is equal to 2%, is equal to the percent added interest. And that's what we're going to be multiplying by each time. So this over here, the amount originally owed is no longer 1,000. It's going to be 1040.04 times 1.02, because we are multiplying the amount originally owed by 2% plus itself. So the easiest way to do that is to pull out your handy dandy calculators right now and pop it into the handy dandy calculators. So doing that calculation, I get 1061.21 cents. To calculate the next term in the sequence, it's going to be 1061.21 times 1.02, which gets me 1082 times 0.43. Now what you're going to see is that you're going to end up with some decimals if you're putting this into a calculator yourself, which is okay. I'm just rounding my decimals to 2 decimal places. The reason I'm choosing 2 in this case is because I am talking about money. So when I'm talking about money, I always use 2 decimal places. Now, if you notice, I stopped writing my multiplication sign and I just started putting the numbers next to each other in parentheses. There are different ways to write multiplication. I tend to just use parentheses instead of the multiplication sign, just because I think that's a little bit less writing for me. So this and this, it's the same thing. Because it's next to something with parentheses, it means multiplication. Just in this case, I used a multiplication symbol. In this case, I didn't. You don't need to include all of this extra work when you're filling out the table, probably just the values. But if you want to check to see how to get it yourself, I would recommend you pulling out a calculator and giving it a go. Okay, let's go on to the next question. A Sierpinski triangle can be created by starting with the equilateral triangle, breaking the triangle into 4 congruent equilateral triangles, then removing the middle triangle. Starting from a single black equilateral triangle with an area of 256 square centimeters. Here are the first 4 steps. So step 0, we have one triangle shaded. I see that. Its area is 256. Step number 1, we have 3 triangles shaded. 1, 1, 2, 3. The area of each one triangle, well, we split the area into 4 spots. So that's going to be 1/4 times 256, which I believe is going to get me 64. But again, if you're having trouble with the math calculations, make sure to pull out your handy dandy calculator to go ahead and do that on your own. Now, how many shaded triangles we had? Well, of each of the shaded triangles, we split each one into 3 boxes. So it looks confusing, but all we had to do is multiply each triangle we had by 3. We now have 9 shaded triangles. The area of each triangle, well, we just talked about that, is 1/4 the area. So this right here is 64, and we split him into 4 triangles. So the area of one of those triangles is going to be 1/4 times 64, which it's time to pull out your handy dandy calculators if your mental math is not quite there yet. Now we took each of these shaded triangles, we split them into 3 more. So this guy got split into 3 shaded triangles. They're starting to look really tiny. And you don't have to let the visually overwhelm it. Notice I'm only focusing on that one triangle in the corner, because if I look at the whole thing, that's going to become visually overwhelming. So each shaded triangle got 3 more shaded triangles. That's 9 times 3, which is 27. And 1/4 times 16 gets us 4. Let's keep going. We don't have an image, but we can do it because we already know we multiply our number of triangles by 3, which get us 81. And then the area, we're going to divide our area by 4, which gets us 1. We're going to multiply 81 times 3, which is 243, and then we divide by 4. And then that gets us our area of each shaded triangles. So if you notice, the more you do it, the more you get used to seeing the patterns, and it actually ends up being quite simple and straightforward, even though when looking at the triangles, it looks pretty complex. Take a second now to review this, otherwise I'm moving on to the next question. Graph, oh no, good thing we have the undo button. Graph the number of shaded triangles as a step, graph the number of shaded triangles as a function of the step number, then separately graph the area of each triangle as a function of the step number. Okay, well, good thing we didn't erase too much. We just erased that 4. So let's go ahead here. We're doing 2 different things. Here, we want the area over step number. And then over here, we're going to have the number of triangles as step number. We went over 5 steps, so it's 1, 2, 3, 4, 5. And here again, 1, 2, 3, 4, 5. The area ranges from 256 to 1/4. So I'm just going to count by 50s because otherwise I'm going to be counting forever. And for questions like this, all you need to do is a little sketch. And the number of triangle goes from 1 to 243. So I'm also going to count by 50s for my scale on this one to make sure I can get all of my numbers in on the graph. So let's start with the number of shaded triangles. When it's step number 0, which is right there, we have 0 triangles. When it's step number 1, we have 1 shaded triangle, which is basically just maybe a tiny bit above. Then we have 3, which is a tiny bit above. That's for step 1. For step 0, there's 1 triangle. For step 1, there's 3. For 2, there's going to be 9, so maybe we'll shift them a tiny higher. For 3, there's 27. For 4, there's 81. And for 5, there's 243. I'm going to connect the dots a little bit to see what it looks like, but you don't have to do that. Now let's go ahead and do the same thing with the area. We start with 256 at step 0, so that's all the way up here. Then we go to 64 for step 1, because it's step 1, 64. That's going to be about right there. For step 2, we're at 16. For step 3, we're at 4. For step 4, we go basically down to 0. This is a tiny bit above 0. And again, you don't have to. I'm going to connect it. So we have this graph for the area and this graph for the number of triangles. They almost look like reflections of each other. So let's answer the questions, keeping those images of our graphs in our brains. How are the graphs same? How are they different? Well, we both see that they're curved graphs that go dramatically up at some point. One started very low and went to high numbers, and the other started very high and went to low numbers. If you need to take a second and go back and look at the graphs now, I would recommend you do that. We're going to move on to problem number 6. A sequence starts with 1, -1. Give a rule that the sequence could follow and the next 3 terms. Well, my rule is going to be, if I start with 1 and I get to -1, I'm just multiplying by -1. So 1 times -1 is -1, -1 times -1 is +1, +1 times -1 is -1, -1 times -1 is +1, +1 times -1 is -1, ... That would be our sequence. Now we want a different rule that the sequence could follow for the next 3 terms. Well, it doesn't say we have to have a geometric rule, so I'm just going to make up my own. I'm going to say 1 minus 2. 1 minus 2 will get me -1, minus 2 gets me -3, minus 2 gets me -5, minus 2 gets me -7, minus 2 gets me -9, ... So that is not a geometric sequence, but it still works, and the rule creates our sequence that we need. All right, that was our last question. If you have any questions, please put them in the comments below, and if you like this video, make sure to like and subscribe so I can see you in the next one.